Hi everyone, I'm glad you're back for more in-depth analysis of the Solow Swan model. So now that we have a good grasp of the dynamics of the model, let's try introducing some more realistic features. The first obvious assumption to relax is that of the stable population. As we've seen in earlier statistics, so population growth has been a staple of the 20th century almost everywhere, including in the US and France. We've seen that fertility rates tend to decrease very slowly, but since the 1950s, the growth rates in the US and France have been relatively stable over time. So the growth rate of population was 1.13 on average in the US. This is thanks to constant immigration. Whereas in France, it was 0.67%. So this rather stable growth rate of population is going to allow us to make a very useful simplifying assumption. So all what we have to see is that population grows at a constant exogenous rate. So we will write it this way. So the change from one period to the other of population is delta L. And to have the growth rate, then we just divide it by the stock, so divided by L. And we see it's constant, so it's just N. If you like France, you see N is 0.67%. And one way that is sometimes written is this way, so we write it G of L. So now we still have few variables to care about. So N is fine, but we're going to introduce more and more variables in the model. And then having this uniform notation G of some variable to signify growth is going to be very useful. All right, so what does that change for us? So just before going for any further, I want to ask you, so what do you think is going to happen to the steady state? Is K going to be still at the steady state constant or not? So I leave you a few seconds to think about it. All right, time's up. So I'm not telling you the answer right away, but just a way to think about it. So imagine a country where population had been constant for a very long time. So capital had slowly but surely reached its steady state value. So it means that, for instance, last year growth was zero. So the investment, which is savings times output, was exactly the same as depreciation, which was delta times K. And now, for some reason, people decide to have children and then they enter the labor market, or some immigrants join the labor market, or they could leave as well. But let's imagine a increase in population. So what happens? Well, the depreciation hasn't changed. It's still delta times K, and we still have the same K. However, there are now more workers in the economy. These workers help produce more output, and a fraction of this output is saved, so it is invested back. So it means that investment is actually higher than depreciation. So we should increase our stock of capital. So if it's just a one-off event, then we should reach a new equilibrium with more population. However, here what we see is that it's a constant growth rate every year. So it means that K cannot be constant in the steady state. As long as people join the labor market, then K is always going to increase. And now, before going to any further, one thing I should say is, so I haven't made any difference between L and so the labor force and total population. Here we don't need to say anything about that. So as we've seen, this share of workers, so the active population, tends to be constant or relatively constant over the long run. So we can just assume that, well, we just have to not care too much about people who don't work. So imagine that this is the whole population. All right. So then, if k is not stable over time, what is going to be stable? What variables are actually going to allow us to keep track of the model? Well, the trick is going to be to not use level variables like k or y, but per worker variables. So these are going to be, for instance, small y equals y over L, and small k, capital per capita, which is going to be capital over L. And the new state variable, so this I'm anticipating, I'm telling you already what is going to be the result once we finish the analysis. But just so you know, the new interesting variable is going to be small k instead of big K. So small k is the new big K, is what you have to think. All right, so how do we know that? Well, for now, we can't really say it because we don't know how L enters the production function. But there is a very neat assumption that we can make, which is going to simplify a lot our lives. And it is the following. The assumption is going to be that f of k and L has constant returns to scale. So what does that mean? It means that if I multiply both k and L by some constant, so say by 2, then f of these new values is going to be multiplied by the same constant. So by 2, for instance. So if I write it, it would be something like f of, say it's a, k, a, L, is going to be equal to af of k, L for some a bigger than 0. So that's a economic way of seeing it. A mathematical way of saying the same thing would be to say that f is homogeneous of degree 1 in k and L. So that means that if I multiply k and L by some constant, then it's like multiplying f by that constant to the degree 1. So here a to the 1. So it means exactly the same thing. So you don't really have to care too much about it. So then what becomes production for per capita? Let's just write it down. So we have small y that is equal to big Y divided by L. And then I just have to substitute F. So it's equal to F of K L divided by L. But then let me write it this way. So it's 1 over L that multiplies F of KL. And now I've just seen that I can, since it's a constant return to scale, I can take 1 over L in front and put it inside the function. So let me do that. So I get 1 over L K, 1 over L L. So then it's easy to see that I get f of k over L is small k and 1. And we're going to define this as small f of small k. Oops, small k. So as you see, this is very similar to what we had before. Before we had capital Y, which was a function of capital K. now we have small y, which is a function of small k. So as you can see, well, you can anticipate that the dynamics is going to look much the same as it was looking. Simply that we're going to be using small letters instead of big letters. So then one thing that I can do to convince you that this is the case is to look at the example we had before. So let's imagine that f of k L is simply the cup de glace with 0.5 or a square root, so it's equal to square root of KL. So that's a valid function. Why? Because it has constant returns to scale. If I multiply square root of, if I multiply K and L by A, for instance, then then I'm going to get well, let me do it. Let me show it to you. So constant to scale. So square root of AKAL equals square root of A squared KL equals to A square root of KL. All right, and then what will be the production? So we will have then y, small y equals square root of KL divided by L. It's going to be equal to square root of K divided, oh yeah, I shouldn't have done that. K, K divided by L, L divided by L. So it's going to be equal to square root of small k. So as you can see, it looks very much like I had before. So before I had the 1, so I had square root of k1, and then everything worked fine. And now I have square root of little k, and there's a 1 here too. So it's exactly the same thing. Now we're going to look at growth rate and then see what the consequences are going to be for the whole new steady state.